3 address code is an example for such a representation. Now in a 3 address code, it takes the form x equal to y OPZ. Here x, y and z are variables. There can be constants or there can be compiler generated variables. So this term, we will see what is meant by that. See, compiler will generate a lot of intermediate variables when an intermediate code is generated. We'll see about that. We'll see how intermediate code, we have a case study on this. How to generate intermediate code for several programming constructs such as if and while loop. Then we will know what's happening. So x equal to y OPZ. X, y, and z are variables, and OP represents an operator such as plus, minus, into, multiplication, or division. Now, the characteristic is that there will be only one operator on the right-hand side. Only one operator. See, our expressions, original expression will be like this. It can be a if statement, or it can also be a statement like this. So here we can see that we have multiple operands and operators in the right hand side, wherein when we go for a 3 address code, we will be using only one operators and operands like this. Now let us take an example for x plus y into z. This is a common expression which will appear in our higher language. Now here, when we represent this x plus y into z as a 3 address code, it has to be in this format, x equal to y OPZ. So we'll take this part first. See, when we convert an intermediate code, when we convert the given expression into intermediate code, the properties of the language will be taken care. So here y into z is to be evaluated first, because these facts we have checked after the syntax and semantic correctness. So y into z will be taken care first. So y into z, it is stored in T1. This T1 is not generated, not used by the actual programmer. Remember that. T1 is a temporary variable which is generated by the compiler. That's what we told. X, y, and z can be either variables, constants, or compiler generated variables. So x, y into z is stored in T1. T1 is a temporary variable. Next, we can see that y into z is added with t, with x. So x, y into z and T1, x plus T1. We store that in T2. Now, can you see a parallel between this and the concept of arithmetic logic unit? When we learn about arithmetic logical unit, we have seen that one operator will be in the accumulator and the other one operand will be in the accumulator and the other operand will be either in a GPR or it will be in a memory location. So you can have one register, one value, say in a GPR called accumulator, and other value can be in a GPR itself, or other values can be in a memory location. And when we add, what it will do? You will see that after the addition operation is being done, result will be put back in accumulator itself. After accumulating result in accumulator, later it is either stored to a memory location or used in subsequent operations. See, this is identical to the machine now. That's what we have told, that an intermediate code, either it can be closer to the higher level language or it can be closer to the machine language that is being generated. So here we have these two temporary variables and one statement. And this is how a 3 address code could be generated. Now, see this is a DAG and this is our 3-address code. So we can say that a 3-address code is a linearized representation of a syntax tree or DAG. And intermediate values are explicitly provided in the help of temporary variables. Now see our DAG in the earlier example for the B minus C example, and this is a corresponding 3-address format for that 3-address code. So here you can see that B minus C is evaluated first, then subsequently the result is being used in other statements to arrive at the final answer. Now we look at different kinds of 3-address statements. One set is unary operations. We know that unary minus and plus plus are examples for unary operators. And how a unary operator can be expressed in 3-address code. We can say x equal to OPY. So here a unary operator will be having only one operand. So there only one operand will be there where OP is the unary operator. So x equal to -3. It can be an example, x equal to -3. Or y is equal to minus of b plus c. So things will like this will come. Here we can see that 3-address code is agile enough to represent a unary operation statement. Now we have copy operations. Copying is nothing but assignment operators. See, we have to copy now. We will have to assign the value of y to x. So here x equal to y. This is available in 3-address code also. X equal to y opz. Here op can be a binary operator, y plus z, like that. It can be y minus z, y into z, and x equal to opy plus y minus y minus y. So all these things are easily expressible using a 3-address code also. Now, what about jumps? Jumping means we will be making use of jumping in control flow statements like if, else code, and loop statements like while. We had an exclusive session on art of programming methodology in our semester 1, where we have revisited our programming knowledge into the way how a program can be expressed finally. There we have had special discussion on control flow statements and loop statements. Both of these statements will make use of jumpings. How jumping will be used there? We know that in an if else then statement, there is a implicit jump for the then part and else part. Depending upon the condition to be evaluated, either we will be executing the then part or else part. Then can be a large piece of code, else can be a code segment. Either of these two code segments will have to be executed. So even if you don't have an explicit jump there, internally there is a conditional jump, and there can be even unconditional jumps when we represent our source code into 3-address statements. So go-to statement followed by a label. Label is an address where the instruction code block is stored. So mere go-to L will represent an unconditional jump, whereas if Y go-to L is example for a conditional jump. And we will make use of all these things when we learned about the case studies of generating intermediate code. Now we have this function call and return. How a function can be represented as in intermediate code. See, f and x1 to xn are n arguments of f. How this will be represented? Suppose that there are n arguments or n parameters in a function. Corresponding 3-address code will be having n plus 1 statements. Each of these parameters will be expressed as with the keyword palm followed by parameters. So palm x1 to xn, n statements for specifying that x1 to xn are parameters. Then we will invoke the function call such as call f comma n. Here f represents a name given for the function and n represents the number of parameters. Now we know that when we write a function, in the body of the function, we have a place where the function body starts and an explicit or implicit return statement. This is how we write functions in high-level language, especially in C. There could be a return statement written by the programmer, or even otherwise also implicitly it will be understood. Similarly here, when a function is a part of a main program and we represent that function in 3-address code, body of the function will be in between the name of the function and a return statement. Between that, the actual body of the function will come. And this is how a function is getting represented in a 3-address format. Now we have array constructs. How an array is to be understood. An array, there will be reading from an array and writing to an array. X equal to A of 5. So here we are reading the elements stored at the ith location of the array, and in the second statement we store back a value to an array. Both of these can be expressed in terms of 3-address statements like this. So it is called as index statements because we know that at least in C, we know how a variable is, an array is represented in terms of a pointer. A of I is same as pointer within bracket, A plus I will close the bracket. I is the index, A is the base address. So hence, this is an index assignment. Similarly, there will be pointer arithmetic also. So see x equal to address of y. Here an address is getting assigned to x. Z equal to value at y. We are accessing the values stored at this pointer address. And w equal to x. If x is a pointer, that address can be pointed by y also. So these kinds of pointer assignment statements are also possible with the help of 3-address statements. So today, hence we discuss about intermediate codes, what is meant by an intermediate code, why an intermediate code is necessary in the compilation phase, and what are the 2 categories of intermediate code representations, and representative examples of high-level intermediate code and low-level intermediate code. We discuss about 2 varieties of high-level representation of intermediate code, syntax tree and DAG. And now we also know about how they differ, especially when common sub-assets are there, how syntax tree and DAGs differ. And we have seen that DAGs are closer to optimizing code rather than a syntax tree. Common sub-expressions will be represented only once. Then we went ahead our discussion on low-level representations of intermediate code, and 3-address code is a prime example for that. What is a 3-address code? How 3-address code can be expressed in various aspects of a programming language: simple assignment statements, copy statements, array statements, pointers, how they can represent 3-address code. That is what we discussed today.